Next up, we are going to look at terminal velocity, which I know you have come across before because you all keep trying to tell me about it, but I want to make sure that we actually understand what's going on and we've got our heads wrapped around it. So before we do that, I just want to quickly review balanced and unbalanced forces. Now I know we've already done this because we've done F equals ma, which required us to think about balanced and unbalanced forces, but it's really important to get your head around, which is why I'm going through it once more. So forgive me for going a little slowly, but this is important. So if we look at the situation that we've got here, I've got 300 newtons to the left, 300 newtons to the right, so I have two equal forces acting in opposite directions, so in essence they cancel each other out, so we could say they are balanced. Because they are balanced, that means that the car will continue to move at a steady velocity in a straight line. Basically, nothing will change. And that is because the resultant force is going to be equal to 0 newtons. Easy peasy, right? Okay, now I've got 300 newtons to the left, 400 to the right. My two forces are unequal, they don't cancel out, so they are unbalanced. That means my car will accelerate. In this instance, it's going to accelerate to the right because there is a resultant force, which I can do by 400 minus 300, so 100 newtons to the right. And that is the force that I would use in F equals ma to calculate its acceleration. It would be that 100 newtons to the right. Right, next one, I've got 300 newtons to the left, 200 to the right. Again, we're unbalanced. Again, the car is going to experience an acceleration. In this case, it's going to slow down, so it would in fact be a deceleration. And the resultant force in this case would be the 200 minus the 300, so that is going to be 100 newtons to the left. Okay. Now, in each of these, I've been dealing with a drag or a frictional force. So drag and friction are very, very similar. They're both forces that come about because they're resisting motion, and we just treat them like any other force. We don't need to stress out about them too much. Okay. So let's think about terminal speed then, terminal velocity. So what we think of is a body that's falling through a fluid. Fluid doesn't mean liquid, just to be clear. So the air is a fluid, water is a fluid. So the way that objects fall in both these mediums is actually very similar. And if we think about it, when our body, our object, is initially released, the only force that's really acting on it is going to be its weight, so the downward force because of gravity. So at the very beginning, the object is going to fall with an initial acceleration of g, because the only force acting on it is the one because of its weight. There is no other force, so it's going to be F equals ma using the weight. So when it first starts moving, it will move with that initial acceleration. Now, as a little note, if we have a particularly dense fluid, we might have some upthrust, which might mean that the initial force at the beginning, there is actually a little bit of an upward force from the upthrust because of the liquid, but we'll talk about that later when we talk about upthrust. But in most situations, when an object first starts to fall, it's going to start with the acceleration of just g, because the only force acting on it is its weight. Now, as the body accelerates, it's going to start moving through the fluid. And as it does so, we're going to start to find some drag. And the faster it goes, the bigger the drag will be, because drag or resistive forces are proportional to the speed at which an object is going. So the faster it goes, the larger the drag force will be. Okay, so the resultant downward force is going to decrease as there is drag being produced. As the downward force decreases, so will the acceleration. So it's going to still be getting faster, it's just going to get faster at a smaller rate. So the resultant force we're interested in here, sorry, I'm trying not to sneeze if you're wondering what the pauses are about. The resultant force that we use for F equals ma is going to be equal to the weight minus the drag, which gives us our mass times acceleration. So our resultant force is the difference between the weight and the drag. Eventually, once it's been going far enough, once it's going for long enough, the upward drag is going to end up being equal to the downward weight. Now once that happens, if the weight and the drag are equal to each other, I end up with no resultant force, so I no longer experience any acceleration. So the downward force is going to be the same as the upward drag, so my object that's falling is no longer getting faster. Now, just to be really clear, because I know this can confuse people, just because the drag and the weight equal each other doesn't mean that my object suddenly stops. It's just that it's reached an equilibrium, so it's travelling at constant velocity. It's just like the car in the first example. The forward and the backward forces balance, so it just travels along at the same velocity. That's what we've got with terminal velocity. Okay, so basically there's no longer any resultant force acting on the body. Resultant force equals 0, so ma, which equals ma, so a must equal 0. So our body is now falling with a constant velocity, which is known as the terminal speed, which is the bit of skydiving that is fun. The bit where you're travelling at the same speed, that's the bit that you want. Okay, so let's just have a little think about what's going on. So what I'm going to do is I'm just going to plot a graph that shows you how the resultant force and therefore the acceleration, because they're going to be proportional to each other, changes with time for a skydiver from when they jump out to when they hit terminal velocity. You may be asked to consider what will happen once they open the parachute. So have a think about that, because we will probably talk about that in class. For the moment, I'm just looking at from the time they jump out the plane to when they hit terminal velocity. So to start with, they're going to have an initial acceleration that's equal to g. That's slowly going to decrease because they're going to speed up because of the acceleration, which means that there will now be a drag force acting on them, which means that the resultant force gets smaller and smaller and smaller as they go faster and faster, and the drag gets bigger and bigger, until we reach a point where there is no resultant force on them anymore. So they start with a large resultant force and a large acceleration, and it decreases as they get faster. Okay, so if we then consider what's happening to their speed, they start with 0 speed, it increases steadily, but it's not a constant increase because their acceleration is changing, so it will curve that levels off, and the point at which it levels off is their terminal speed, their terminal velocity. Okay, so that's what's happening to the speed. It gets up, 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 bigger and bigger until we reach our leveling off point with terminal speed, and our acceleration starts high and decreases until it goes down to 0, because it's only when we've got 0 that we can have our terminal speed. Okay? Have a think about how this graph would continue to go if we then open the parachute. So we're going to talk about that in class. So either come to next session with a sketch of what it will look like, or come in, grab yourself a whiteboard and sketch it straight away. Okay? And I will see you then.